So welcome to the Out of Normals time NetSeminar. We have a very good speaker from Columbia University, Professor Vishal Misra. And actually, in advance, I'm going to announce a double feature today. Second seminar following this at 4:15 in Packard 101 is Professor Moore-Hartle-Balter from CMU. So it's a big networking day at Stanford with two East Coasters. Vishal was a student of Don Towsley's from Amherst and was amongst the first few people, if not the very first paper, on fluid models of TCP that came out with the congestion control mechanism modeled and analyzed in the control theoretic sense. This is simultaneously there were papers also by Kelly and Lowe, but they were looking at it from an optimization perspective, where this was a control theoretic analysis of TCP with lags and stuff, which had a huge impact on the field for the next, even now it's going on, but certainly on all the TCP algorithm designs and analysis were taking place. His paper was required reading. So with that introduction, he's been doing a lot of interesting stuff on network neutrality. I'll leave it to Vishal to tell us what it's about.
Thanks, Balaji. So thanks again for inviting me here. This is work that we started doing 6-7 years ago, and at that time we were saying, what are you doing? What's this network neutrality? What has it got to do with networking or engineering? And now, thanks to President Obama or John or whatever, people are talking about network neutrality. Suddenly it becomes interesting. So this is joint work with my student Richard Ma. He's now faculty in Singapore, NUS Singapore, and colleagues Alvin Chu, John Louis, and Dan Rubenstein. Now, when I say joint work, I say it in the loosest possible sense. This work was really driven by Richard. It was his idea. He pushed for looking at things in this way, so all credit should go to him. He was the one who drove this work. So the title of the talk is, network neutrality debate and engineering perspective. I'll talk about it. I'll give you some details. But if there's only one thing that you want to take away from this talk, it's this first slide. So this is a conversation that happened about 15 years ago between a very prominent economist. He prefers that I don't name him.
But we know who it is.
You know who it is, right? And Dave Clark. So Dave Clark tells this story often. Dave Clark is one of the foundational architects of the internet. And this was friendly banter between friends. But the economist feels people might think that I'm criticizing you guys. That's not my intent. But the conversation ran like this. He said, the economist said the internet is about routing money. Routing packets is a side effect. And then he said, you guys really screwed up the money routing protocols. Dave Clark said, well, we did not design any money routing protocols. The economist said, that's what I said. So if, the whole network neutrality debate is all about, what's there in this slide. It's a fight over money. People talk about innovation and, freedom, and, 4 million people got excited about the FCC ruling, and they wrote to at the FCC thinking they were fighting about freedom. It's a fight about money. And that's what I hope I'll convey in this talk. I often say that network neutrality is a symptom. The real problem is elsewhere, and that elsewhere is what I'll talk about.
Dave Clark said, I think, in his paper, a similar thing, where he didn't realize that by designing the technical interfaces, he's also designing the business interfaces.
And that was the problem. Yeah. So, the economist, great insights here. And I discovered this conversation a couple of years ago. And I said, this explains what we have been doing completely in one slide. Okay, so let's start with the work. So rest of the talk, I'll talk about the background of the work, how we got started. Then I'll talk about cooperative game theory and Shapley values. That's sort of the lens that we have used to look at this problem. I'll talk about the application of Shapley values to peering between ISPs. I'll talk about the instability of settlement-free peering, which really is the core of the fight between Netflix and all the ISPs that has been happening over the past couple of years. If I get time, then I'll get to something that we analyzed recently, paid prioritization, which now the FCC has said you cannot have. But we did some analysis of paid prioritization in different scenarios, scenario of monopoly, oligopoly, and what we propose an alternative called public option, which is not network neutrality, but it's kind of community or municipal broadband or a publicly owned infrastructure. And if I get time, I'll show you why that has some really nice property. And all that you want from network neutrality you can get from that without any of the regulations. But so let's start with the first part, which is ISP settlements and Shapley values. So the way we got started was we were doing conventional networking. We were looking at peer-to-peer networking. BitTorrent was really hot. 2006, 2007, that time frame, and there were lots of things happening. ISP started dropping BitTorrent packets based on port number. ISPs identified, this is BitTorrent traffic, or it's running on this port. Let me drop it. I'll drop it. Then users started doing dynamic port selection. ISP started doing deep packet inspection. They used to look inside the packet, look at the header, then figure out this is BitTorrent, let me drop it. Then the user started encrypting the BitTorrent traffic. ISP started doing behavior analysis. We use machine learning technique using the inter-packet spacing to figure out, okay, this is P2P traffic. So this whole cat and mouse game was going on. Comcast started throttling BitTorrent traffic. This was sort of the start of the whole network neutrality brouhaha in the US. The first real case of network neutrality violation. And it became evident to us that the problem was rooted in economics, not engineering. These are engineering solutions and countermeasures that were going on. But we realized that we have to look at it from an economics perspective. Why are the ISPs really doing it? So
throttling is a nice way of putting it. They actually forged closed connections.
Yeah, they send reset packets, right?
They send reset packets, exactly.
So then he said, well, let's find out what the economists are saying. And we found some papers by economists looking at this problem. And they said, let the internet be a two-sided market. On one side, the consumers, and the other side are content providers. But if you know about the internet, it's not this simple picture that there's a two-sided market and the ISP is sitting in the middle. The internet is a lot more complex. There are multiple ISPs, there are multiple peering arrangements. There are eyeball ISPs, there are transit ISPs, there are content ISPs. So it's a much more complex system than what the economists had been looking at. And just to give a little bit of background of what the ISPs are. ISPs are autonomous business entities. They want to make money. They provide internet services. All of them are trying to make profit. And Dave Clark actually gave this taxonomy of ISPs. Said the ISPs, there are three kinds. The first is the eyeball ISP. It provides internet access to consumers, residential consumers, or even universities or companies. So these are the eyeball users who get internet access through eyeball ISPs. Second kind of ISP is the content ISP. So these serve content providers. So they're not directly connected to the eyeballs, but the content that the eyeballs are consuming, these ISPs connect to the content providers. And I'm including CDNs in this definition of content ISPs. A lot of these ISPs, like level 3, they are basically CDNs. And our Netflix has created its own CDN. So you can classify Netflix as a content ISP. The third kind of ISP are the so-called transit ISPs. They provide global connectivity and they provide transit services for these other ISPs, for eyeball ISPs, content ISPs. So examples of tier 1 ISPs are level 3, AT&T, Telefonica, Tata. Now some of these ISPs play multiple roles. They could be eyeball ISPs as well as transit ISPs as well as content ISPs. But just to sort of have a clear mental model of what's happening, we'll treat them as different entities. It doesn't really matter if they play multiple roles, but for the sake of sort of analysis here, we'll say that they are different kinds of ISPs.
When does a company shift between Class B and Class C? Is it just the amount of data they transmit, or the amount of clients they have? What's that cutoff point?
It's the amount of peering they have. So it's not really the volume of data, but the amount of the number of clients. So then we looked at, this is where Richard came in. He said, why don't we look at this issue from the point of cooperative game theory? So what are cooperative games? So in cooperative games, the way these ISPs come together and help create the internet, you think of a cooperative game as a coalition where a bunch of different players come together and create some value. So you can imagine this is the value that is being created by the internet, and you have all these players. So you have, let's say, n players. They generate some value B, and you also can think of coalitions where you can have subsets of these players, and then you can think about the value that this subset generate. So different subsets will generate different values. You can have different coalitions and a value associated with that coalition. And the field of cooperative game theory, it analyzes coalition formation given a value allocation. So the idea is that you have this coalition of players who get together, they generate some value. Now you have to divide that value amongst the players. And cooperative game theory looks at how coalitions form given what the allocation function is. And this value allocation characterizes the solution of a game. So the way you're going to divide the value amongst the players, that's a value allocation, and that's also called a solution to a cooperative game. So some properties of interest in a solution is one is stability. So you want a solution where players do not want to deviate from the solution. A solution or value allocation exists, so players are happy being part of the solution, or at least not unhappy enough that they want to leave. Second is you want to look at the fairness of the allocation. So you want the allocation to somehow reflect the contribution that each individual player makes in generating that value.
So how do you evaluate? How can this value be sort of objective when different people place sort of different subjective values on a particular thing?
So you, at a very coarse level, you can just look at the revenues or the profits. Think of it as the money that's being generated.
Right, but there's certainly lots of people post things on Facebook. They don't get paid. Facebook doesn't pay them. Facebook gets money from them. Their friends don't get paid. They don't, I mean, there's a lot of, I guess, sort of non-paid exchange, right?
Right. So they are in Facebook because they are getting some value out of it, or they would have left it.
Yeah, and that value is not necessarily the amount
equal
to the revenue that Facebook gets from their page.
No, so here I'm talking about the business entities who are actually investing money and getting money out of the system, not users who are sort of. That'll come into the next slide.
Users are investing; they're paying their ISPs, right, to get some value. So
yeah, so
they're investing value, and they're also
so that money is part of the formulation.
Okay, so you're just looking at money, basically.
Which I'm just looking at money here. Internet is about routing money. So a subset of these cooperative games are so-called convex games. So what are convex games? The convex games, B is said to be convex if for all coalitions A and B, the value generated by the coalitions satisfies this equation. But you can also describe it differently. You can say that the marginal contribution of a player increases with the size of the coalition it joins. Another way to put it is sort of the network effect. There are all these natural models for networks, and there are these folk laws. There's Metcalfe's law, which says the value of a network of size n is n square. But let's go modify it and said, the value of a network of n nodes is actually n log n. I mean, their value outside the game is less than their value inside the game.
Right.
So for a convex game, you always have a set of stable solutions.
So it seems that V is dollars, right? Because you're strictly talking about money.
You're talking about money.
So my understanding is that in this game, the only people who give money are users, right? End users or not?
No, so the coalition generates some value. So in the internet example, the value is being generated because people like us are paying ISPs the monthly charge, or the Googles and the Amazons are paying the content ISPs money to carry their traffic. But that is the value that is being generated, and then the question is, how do the ISPs divide that value among
So are the users, me as a user, am I part of the coalition?
No. We're talking about the ISPs.
So my satisfaction in this whole game, it's not part of the equation.
No. Okay. You're paying your ISP whatever you're paying.
Okay.
And it comes into the picture. I'll talk about it.
So the utility that I'm getting from this network, it's not
part of that. Okay. It's just the money that is being generated.
Okay.
So just one last thing.
Yeah.
A coalition can be thought of as a collection of subsets of a set of n players.
Yeah.
Where there can be obviously overlaps because you're allowing intersections. That's it.
Yeah.
Okay.
Yeah.
If I may, you said we have the functions V of A, V of B, V of C. Are they independent? Generally, the value for A is dependent on how B and C perform the task or not.
So they're not independent. They depend on God B. And I'll give more examples where it'll become clear how they depend. So you have these, you have a convex game, and we say that the internet or the network is a convex game. In a convex game, you always have a set of solutions which is stable. It's called the core, and the center of gravity of this core is called the Shapley value. So you can think of the Shapley value as the most stable of all solutions. So if your solution is somewhere here, then it's sort of borderline stable. Little perturbation, and some players might be unhappy and they leave the game. If you get the Shapley value, then it is the most stable solution, and I'll explain why that is. Well, that's the case. Another way to visualize is, suppose you have two players. On the x-axis, I'm plotting the value generated by player 1. Y-axis, the value generated by player 2. The value generated by player 1 individually is A. The value generated by player 2 individually is B. And we assume that when they get together, the value that they generate C is greater than A plus B. So this is convex in that sense. So here the core is this red line. If you have any value allocation along this red line, both A and B are getting more than what they were getting when they were in their own coalition, when they were operating individually. But if you have a value allocation here, then the first player is happy. He's getting more than what he was getting individually, but the second player is getting less than what he was getting individually. So the second player will leave. And this is why this outside the core, you're unstable. Similarly, if you give a value allocation here, player 2 is happy, but player 1 is unhappy, player 1 will leave. But if there's any allocation along the red line, then both of them are getting more than what they were getting individually, so they'll stay in the game. And the Shapley value will be the midpoint of this. This is a very specific example. So Shapley proved that the core is a convex set. The value is located at the center of gravity of the core. So what is this Shapley value? So Shapley gave an axiomatic characterization of this Shapley value. So Shapley value in some sense is a measure of one's contribution to the different coalition that it participates in. And when Shapley proposed the Shapley value, he proposed it in terms of these 4 axioms: efficiency, symmetry, dummy, and additivity. Then Meyerson in 77 replaced dummy and additivity by this axiom called fairness. And then Young in 85 replaced fairness with strong monotonicity. But all of them are equivalent. As long as you satisfy axioms along one row, you will get the same value, which is the Shapley value. Now, all 3 of them received Nobel Prizes for different things.
Just to, these properties are satisfied by what?
The solution. I'll explain what.
A solution is the Shapley value.
If it is yeah. So what I'll do is I'll explain the solution in terms of the Meyerson definition. But all of them are equivalent, and all of them yield the same unique Shapley value. So, so let me first explain what efficiency and symmetry are. So you have this correlation, they come together, they generate this value. Efficiency simply says that there is no loss in the distribution. Right? So what you're saying, B1 through Bn equals P. So you allocate whatever you generate to the players. Very sort of intuitive, obvious axiom. So all profit goes to the players. Efficient symmetry says identical players get equal shares. So if you can define identical behavior in some way. So here I'm just doing color coding. So all the blue players, they are identical in some sense. They're all getting 1 unit. All the red players are identical, they get 2 units. The green player, if there were more, they'd all be getting 3 units. So that's what symmetry says. And if your impact on the system is the same, then you should get the same value. So, identical players get identical values. The fairness axiom or the balanced contribution axiom, this you think in terms of pairwise behavior. So let me walk you through this axiom. What it says is, you have a coalition and you generate some value, and then you have some value allocation. Okay, so you have the value allocation, whatever means you achieve that. Now let's say you focus on one player, and let's say another player joins the coalition. When this player joins the coalition, the value allocated to this player increases by a certain amount. Okay, so what happened here? The value allocation for the blue player, we are focusing on that. It increased by 2 units. The balanced contribution axiom says that when blue leaves, the value allocated to green should get reduced by the same amount. It essentially says what I do to you, you are doing to me. So it says that if blue had entered the coalition, the value of green would also have increased by 2. And you do it for every pair. That's what balanced contribution or fairness is. So you look at every pair, and what one player is, the benefit one player is bringing to that other player, the same benefit that other player brings to this player. So if you have any value allocation that satisfies these 3 axioms, efficiency, symmetry, very sort of obvious. Balanced contribution, it makes sense that it's a measure of fairness. If you satisfy these 3, then you get the Shapley value. Let's now come back to our original problem of looking at the ISP and see what is a fair solution in that sense. Let's try to apply the cooperative game theory ideas here. So we start with a very base case. You have one content and one eyeball ISP. So you have the content ISP serving, let's say, YouTube, the eyeball ISP serving its customers, and that's the entire ecosystem. And profit V is the total revenue that is generated, content side plus eyeball side. You can subtract the cost, but let's say that's the total revenue. And you can have content side, you can have revenue in terms of per byte. On the eyeball side, you can have a flat rate per month. It doesn't matter. You're just looking at the total revenue that is being generated. Yeah.
So it seems that you take for granted that we know the value V and we try to split it between the players. Mm-hmm. And my understanding is that the whole debate is about what is this value V, right?
I'll come to that. So don't think of the Shapley value as a prescriptive solution that you have to do things this way. Think of the Shapley value as something to compare against. If the actual solution gives you something which is close to the Shapley value, then you know that the solution is going to be stable. But if the actual mechanisms that exist on the internet yield you a solution which is far away from the Shapley value, then you immediately know that there's something wrong, there's something unstable. You need to do something different. So you need not know the exact value, but whether we are in the neighborhood of Shapley value or not, that's what we're going to do. So don't think that I'll say that you need to know the exact revenue and then there's some authority which distributes the revenue. Okay. Think of it as a mechanism which is telling you something about the stability of the solution.
What's sort of worrisome about this is you sort of base it on profit, and sort of profit sort of depends on kind of the financial aspects of your business, how efficient you are.
Yeah.
Obviously, non-profits generate no profit at all, so because they just reinvest in their company.
Right.
I mean, Amazon's a non-profit sort of because they usually lose money.
Not a long. That's a separate debate, but you can say that most ISPs are there to make profit, right? And Amazon is paying its ISP to carry traffic.
Even for something like Wikipedia, you can equate anything. You can put a dollar value. You can ask for a declarative thing of a dollar value for anything. What's the value that Wikipedia gives its users? They can ascribe something to it, right? So it's not. There's a method of thinking here that economists will evolve with, like, that is consistent with itself. Right? He's just using it.
Yeah, I mean, it doesn't have to be hard dollar profits.
But this is the way they're analyzing this, right?
Yeah, it seems that the model isn't really a good match for reality in a lot of sort of dimensions. But yeah.
Let's see what
Let's carry on with the thinking. So
I would consider sort of matching the model a little bit differently to the way you present. But anyway, go on.
Yeah, we come to questions. Yes. So in this scenario, if you have this, the total value generated is V. You can apply the axioms, and the Shapley value solution is you split the profit equally. The content ISP and the eyeball ISP, they should get half of V. Okay. Nothing surprising about that.
Oh, it's pretty surprising to me because it's irrespective of the costs that each.
No, so I'm saying you extract the profit. This is the profit. It doesn't matter.
But like
you
a
can
one-person company versus a 1,000-person company, you're saying that they should split it.
Yeah, because what happens is if you take away any of the ISPs, if you take away the eyeball ISP, there's no one to watch that content.
Right, but
if you take away the content ISP, then there's nothing for the eyeballs to get from the internet.
There's this idea of capital expenditure and substitutability, right? If one guy owns the infrastructure and another guy is just instances in a cloud, like one's a lot more replaceable than the other. And so there's an implicit assumption of substitutability, which really doesn't seem to match reality.
In this case, there is no one who's replaceable, right? If you take away the eyeball ISP, then the content ISP has no way to reach the customers.
Well, if we could get rid of YouTube.
Shall we keep all the questions for the end, because we're gonna run out of time?
Yes, let's move on, because talk to him afterwards. Because we have another seminar to go to.
Right. So I mean, here both are V2 pairs, both get half. Now let's change and add another eyeball ISP. So how should the fair profit share change? Previously, one content ISP was getting half V, one eyeball ISP was getting half V. What should the new? I'll give the talk like more always ask these questions. He'll ask the audience to solve. But what would you guess?
Should probably all get half.
All get half?
Yeah.
Okay. You normalize that and you'll say everyone should get a third.
Okay. 0.25, 0.25 and half.
So who should get half?
C1.
C1 should get half, and these two should get 0.5. So let's apply the Shapley value axiom and see what we get. So you apply symmetry. The eyeball ISPs are symmetrical to the system. They're providing the same value, so they should get the same value. You apply efficiency, and you get, so far, half and 0.25 works. Then you apply the balance contribution axiom. And what we are looking at, let's say B1 was the eyeball ISP that joined the system. Pbefore B1 was there, the content ISP was getting half of V. Then B1 joined, and phi C1 is a new value that the content ISP is getting. Now the balance contribution axiom says that this difference should be the same as this. This eyeball ISP was not getting anything before it joined the system, so it had value 0. Now it's getting phi B1. When you solve that, the Shapley value solution is actually the content ISP should get 2/3, and both of them should get 1/6. So you were there, but it's actually worse than what we think. The leverage of the content ISP is much more than what we sort of think, and it is the axiomatic solution. So according to the Shapley value solution, it is the fair solution. It is the stable solution.
That doesn't make any sense because if B1 or B2.
We'll keep going. Yeah.
Let them go on.
Yeah.
So the theorem, what we proved that if you have a situation where you have n symmetrical eyeball ISPs and one content ISP, then the share of the content ISP goes to n over n plus 1. It's getting almost all the profits. and the eyeball ISPs, each one of them is getting 1 over n times n plus 1. So the marginal value of these eyeball ISPs is reducing dramatically faster. And why it makes sense is, if you have more eyeball ISPs, then the content ISP has a lot more leverage. Because the eyeball ISPs, they are sort of interchangeable. If one goes away, you can move to the other. But there's only one content ISP. It has veto power over the system. That's why intuitively it makes sense. And what the actual numerical value according to the Shapley value is what we show here. So the marginal profit loss that an content ISP gets when an eyeball ISP leaves is 1 over n square when n is the number of eyeball ISPs. If n equals to 1, then we revert to the base case. If you have multiple eyeball and multiple content ISPs, we can show that the profit share is if you have m content ISPs and n eyeball ISPs, the formulas are listed there. What they basically say is each ISP's profit is inversely proportional to the ISP number of ISPs of the same type. So that's the competition it's facing, and it's directly proportional to the number of ISPs of the other type. So that's the leverage it has on the other side. So the more you're competing, the less is your share. Again, very intuitive, nothing surprising here. It's just that we have given numbers to these values. Then when you introduce transit ISPs into the equation, things look a lot more complicated. The formula looks hairy, but the intuition remains the same. If you work out the formula, then you plot the graphs, the exact intuition continues. You're better off with fewer of your kind and more of the other kind. Okay. So this is what the Shapley value says, and then we look at how do ISP businesses actually work. There are two common forms of bilateral settlements between ISPs. So you have these content eyeball transit ISPs. Content ISPs having content, customers are paying it. Content ISPs buy transit services from transit ISPs. Eyeball ISPs, similarly, they are serving customers. They buy transit services from transit ISPs. These transit ISPs pair with each other. The norm used to be $0 pairing, where these ISPs would simply exchange traffic, and not charge each other anything. When we were doing this work, that was the norm. So now we look at this thought experiment of how do you achieve a stable solution, theory versus practice. So the theory of the Shapley value theory says, you generate all this revenue from the eyeball side, from the content side, and then what you do magically, you distribute it amongst all the players. That's how you get the Shapley value solution. In the real world, you don't have this sort of multilateral settlement. You have bilateral settlements between entities that directly talk to each other. So either you have, eyeball ISPs talking to its transit ISP, or transit ISPs talking to each other, or transit ISPs talking to content ISPs. And the payment is always in one direction. So I don't know if you remember, 10, 15 years ago, Lishan Gao had this whole valley-free property of the customer-provider relationship between ISPs. So transit ISPs were always selling bandwidth to eyeball ISPs and content ISPs. So there were no valleys. So the money flow was always in the direction upward. You can think of it as a tree rooted with transit ISPs. So this is a reality. That's the theory. Question is, can this approximate the Shapley value? So I'm not saying that you do the Shapley value, but if your actual process leads to a solution which is somewhere near the Shapley value, then you have a reasonable system. So what we realized was that when content side revenue is approximately equal to the eyeball side revenue, Then the customer provider settlements where the transit ISPs are selling bandwidth and $0 pairing settlements, they could lead to a solution which was close to this Shapley value. So this is a scenario, if you think 15, 20 years ago, when the internet was basically some educational institution, some research institution exchanging light email and web traffic with each other. The amount of traffic flow was symmetric. The amount of revenue generated was symmetric. So these $0 pairings worked. Then when well-defined content providers entered into the picture, then two things happened. Firstly, the direction of traffic changed dramatically. It was heavily from the content side to the eyeball side, and it also generated this stream of revenue which existed because of the internet, but outside the internet, right? The Netflix charges that we pay, it's because of the internet, but it's you're not paying the ISP directly. So this whole stream of revenue started, and the content side revenue became much higher than the eyeball side revenue. And the implication of that was you needed reverse customer provider relationship or paid peering. This is what we said, 2008, 2009 when we wrote the paper, that according to our analysis, the ecosystem is unstable. It's the solution is, from whatever data that we could gather, it's outside the core. It's unstable, and you're going to get these disputes. Another thing that matters quite a lot is when the customer side competition is much lower than the content side competition, the same effect happens. The formula that we had, N and M. So the lower N is compared to M, the more sort of lopsided the system becomes, and the more you need money to flow in the reverse direction. The transit should be compensating the eyeballs. So in the old early days of the internet, the commodity that was being traded was bandwidth. You bought and sold bandwidth. Now what has happened is implicitly the commodity that is being traded are the eyeballs. The e-commerce or the revenue that is being generated by the consumers, that's really the commodity that's being traded. So that's why to achieve a stable solution, and because there's no competition, you need these reverse customer provider relationships, and paid pairing we said will emerge. And so the internet changed where you had revenue sources within and outside the internet. You had these outside flows between content providers and eyeball ISPs. So two things happened. First, the revenue on the content side increased. Secondly, in the US, competition at the last mile is minimal to none. So both of these factors make the eyeball ISPs a lot more dominant. Yeah.
Can you explain what customer side competition is?
So how many ISPs do you have as a choice at home? Most people have one or two. Right? Most people have one. Whereas on the content side, it's much easier to pair with a large content provider. So multiple tier 1 ISPs, multiple CDNs can go to a content provider and make them their customer. It's much easier. It's much harder to go and dig the last mile everywhere. So the level of competition in the US has remained very low on the eyeball side, but on the content side, there's heavy competition. So the transit prices have reduced by 2 orders of magnitude in the last 10 years. Whereas neither the level of competition nor the amount we pay for our broadband has reduced the eyeball side.
So the fact that the bandwidth is so much lower on the last mile, does that affect any of this, or is that really irrelevant?
It's really irrelevant.
It just doesn't matter for
It doesn't
for
matter.
your equations, right?
Yeah.
So you're saying something very counterintuitive, which says that the more content providers you have, the worse it can become for the user, because the ISP gets much better.
Because we have no competition. Yes. Right? So,
Well, there's sort of a reason for that. I mean, it's usually they're government-established monopolies, and the idea is that they accept government regulation in return for getting monopoly profits. And
in the US.
Yeah.
In the US. Yeah. So what Netflix ended up doing with multiple ISPs is, instead of pairing at these public pairing points, they started these paid peering connections with broadband ISP. So they signed paid peering arrangements with the top 4 ISPs in the US, and all those 4 ISPs happen to be local monopolies. So what has happened in the US is that all these ISPs, Comcast, Time Warner, Verizon, AT&T, they went to different markets, they dug the last mile, and the first person to dig the last mile had an advantage. So nobody else went there and dug the second last mile. So what we have in the US, we have these islands of monopolies. So all these ISPs are actually monopolies in their area. When the Time Warner and Comcast merger was proposed, the CEO of Comcast said, this will not reduce the level of competition because we don't compete with each other. that's not a reason. That's a question. You are billion-dollar companies. Why aren't you competing? So they have just created these islands of monopolies and then don't compete, and that's why Comcast or these ISPs can use their customers as leverage to extract revenue from content providers like Netflix. So Level 3 had this big blog post last year where part of the data that they showed was this. This is the percentage change in Netflix download speed since January 2013 by ISP. This is the date where Comcast started its paid peering arrangement with Netflix, and you see the difference. Same thing happened with all the other major ISPs. Those ISPs, Cablevision, Cox, Google Fiber, they did not have paid peering arrangements with Comcast. They were never monopolies in their market. Instead, what they did was they accepted Netflix's CDN. Netflix started this Open Connect CDN. They said, okay, yeah, put your servers in our network, and performance was much better.
Cox is actually a monopoly in their market. They're a cable company.
Cox, well, I don't know. Cox, but they accepted Netflix.
Right.
But these ISPs said, no, we're not going to. So the performance of Netflix, actually Level 3, really became bad in the network, but they didn't care because the customers had nowhere to go.
Yeah, but the question, the difference is not that they weren't a monopoly, it's they actually use their power, basically. They use their monopoly power.
Yeah, they use their monopoly power. And Level 3 had this, besides this, they had these graphs where they showed that they had like 55 different peering links, except for these 4, which are monopolies. Every other link was running at 30% or lower utilization. These links were consistently running at 90-95% over a year. Huge amount of packet drops, huge amount of delays, but these ISPs did not do anything until one by one, all of them signed a paid peering arrangement. So what implicitly the paid peering arrangement does is it transfers part of the Netflix revenue to the eyeball ISPs. And if you think in terms of the theory, it moves the solution back into the core. Now, in some sense, it is a fair solution, but this is not the right solution. And all this debate about network neutrality, I feel the real problem or the real issue is competition at the last mile. That's what the focus should have been. That's where the effort should have gone into, instead of these regulations about Title II or no blocking, no throttling. Nobody was really doing any blocking. People are saying no paid prioritization. Nobody was doing any paid prioritization in the last mile. What they were doing was these paid peering, which is not covered by net neutrality. So even with the new rules, you still have this paid peering. It amounts to a paid prioritization, but not at the last mile. So the analogy that I gave is you lock the door of your house very securely, but you leave the windows open. The problem is not at the last mile. The problem was created at the peering points. That's what the ISP is exploited, and that's what they can continue to exploit. Yeah.
Is the argument about competition true for like other countries like India, where you have like a lot of ISPs?
India is a separate story.
Yeah, it's true though, right? You're following all this Airtel blocking Skype.
Yeah.
Right?
Well, not Skype. Airtel had proposed something called Airtel Zero.
Yeah.
So zero rating is an actual problem. FCC completely ignored it. They talked about paid prioritization, throttling, blocking. Nobody does that. Blocking and throttling is done by governments, not by ISPs. ISPs want to make money.
What about BitTorrent that you mentioned?
That was all about making money, right? So if you had competition, then so what happened in the UK? The UK is an example where there is thriving competition in the last mile, and initially, everyone has a choice of 4 to 5 ISPs, 3 or 4 of those ISPs were actually doing traffic management. They were slowing down BitTorrent traffic. One ISP, Sky, said we're not going to do any traffic management. No traffic management at any point. Slowly, all the rest followed. So that's the effect of competition. Because the customers had a choice and they started moving to Sky, they got a better reputation. All the others followed.
It's reminiscent of the old DSL line sharing agreements that no longer exist in the US.
So that's the local loop unbundling. Something like that should be tried, and that's something that actually, how do you price that? That's a separate topic. So how much time do we have?
Yeah, 5 minutes.
5.
Maybe
Yeah.
5 minutes.
5 minutes.
So I'll quickly talk about paid prioritization. We analyzed this issue of paid prioritization at the last mile, and similar to what we saw, how economists treated paid prioritization, we saw that economists looked at paid prioritization and they said treat the internet as an MM1 queue. And I had no idea what was the first term, what was the second term. Are you talking about packets, flows? They said that the queue size is your QoS, and there was some analysis based on that.
You said, who said this?
Economists. There are papers from economists. Actually, one of them is called Big Report. So what we did, we developed a more careful model of the topology. We developed a more careful model of the traffic, the congestion control mechanisms like TCP, flow, maximum fairness. We also tried to model different kinds of traffic, where we said different applications have different unconstrained throughput. Netflix will have a much larger demand than Google search traffic. We modeled the different popularity of contents. We also modeled something called the demand function of the content, where what we said was if the achieved throughput for an application falls below the required throughput, at what rate do the users leave? So the figure, this curve on the extreme left would be for the Netflix kind of traffic. As soon as your throughput reduces even slightly, users will start leaving, the quality suffers. Whereas you're much more elastic for, let's say, search traffic. So we did this kind of careful modeling, and I'm not going to go through the math of the analysis for monopoly. I'll just give you the final result of what we analyzed. What we did was, we proposed this thing called a public option ISP. We said, let there be an ISP that voluntarily implements network neutrality where there's no paid prioritization. And let's see how the system evolves in the presence of this public option ISP. And I'll present the final result of our analysis. I'm happy to talk to anyone offline. What we showed was if the internet is a monopoly, which it is in a lot of markets, then the best thing to do is have the public option. Create a public option. The next best thing is you should have these network neutrality rules where no paid prioritization is allowed. Every packet should be treated the same, and so on. In a monopoly, having paid prioritization is a bad idea, because we show that there is an incentive for the ISPs to create the scenario of damaged goods, where the free portion of their links, they can severely constrain them that you're forced to move to the paid part. And that's essentially what Comcast and Verizon did with Netflix. The free public peering, they became so congested that they had to move to this paid peering. Now that doesn't come under the definition of paid prioritization because it's not happening in the last mile, but the effect was the same. So if it's a monopoly, we say that, yeah.
Just say in this count, what is public option?
So public option is an ISP, one ISP that says I'll be network neutral.
Why is it better than net neutrality?
Because we show that there are some cases where you want some quality of service, you want some differentiation, but the presence of the public option keeps the ISP that's providing that differentiation honest. So one size doesn't fit all, depending on the shape of your demand function, the demand we had sort of extensive modeling and simulation, and we showed that the public option gives you the presence of the public option forces the ISP to behave in a way consistent with the user utility. So the social welfare is maximized. But if the public option is not there, then the ISP will maximize its own utility and not care about the public utility.
I mean, just to be, sorry, if you have different classes of traffic is requiring different things.
Yeah.
Like voice versus datagram. How can public, what are you saying? That public option means just treat them both equally or
Treat them both equally, yeah.
Treat them both equally.
Yeah.
Great.
Yeah. But what we say, if you have real competition, then forget public options, competition takes care of it. And if you have competition, then network neutrality is actually bad. What has happened with the new FCC rules, they have said that if you have a public IP address, then best effort is all that you can get. You cannot have different quality of service for different classes of traffic. So the FCC has said, no blocking, no throttling, no paid prioritization. If you have a public IP address, you can't get anything better than paid, better than best effort. Which, as networking researchers, we know that different applications have different requirements. As long as you differentiate, you're good. When you start to discriminate, then the problem arises. So as long as you differentiate based on the class of traffic, it's okay. But if you start discriminating based on the origin of the traffic, that's where these problems occur. But what FCC has said, no, nothing.
I think the FCC leaves a window for user-based differentiation, right? User-driven differentiation.
But unless you have something happening at the other end, there's very little the user can do, right?
Right.
Suppose you want a low latency service. Okay. How can the user manage
the user
low
just
latency?
says that I want this service to be low latency.
So they have to create special peering arrangements and.
No. You can decouple the two, right? The ISP can provide the low latency service, and then the user just has to map the traffic to that service. The user doesn't need to be aware of how I set up my router and everything. The network says low latency, just put a bit in your packet, and I will treat it as low latency.
Exactly. The wiggle room that they have left is they have this special thing called specialized services.
Mm-hmm.
Specialized services can have different quality of service.
Mm-hmm.
Anything with a public IP address, they said no. Okay. So if your cable company is sending you your television traffic on IP, the cable company is allowed to prioritize that. Mm-hmm. If your cable company has your voice over IP, their own telephone system, they can prioritize that. Skype cannot do that. OneEdge cannot do that, which is a problem. And
in the remaining 2 minutes, I was wondering if I could ask a sort of bigger picture question. So this is, I think, a really nice analysis of sort of what we should expect economically from the status quo. I'm curious, what if, from a system building perspective, what kinds of avenues do you think we should be working on as new systems we should engineer to try and improve things?
So we should be going towards having more competition. Now there are different ways to achieve competition. The model that the US has followed is facilities-based competition, where you have multiple last miles and you compete based on that. The model that other places have followed and have been actually quite successful is service-based competition, where the last mile is a shared infrastructure, and then they can lease that last mile access to any ISP. Then the ISPs compete based on service. So this is the model that the UK has with their British Telecom Open Reach system. British Telecom, BT, owns the entire infrastructure, but they act as a wholesale provider to ISPs. So Sky, Virgin, Talk, they all lease. And so that's why that's sort of a better way to get.
Really keep answering Keith's question.
No, so we should be looking at mechanism where you can have this leasing at a higher layer done easily. There are technical problems to be solved there as well. So at a system level, we should be looking at how do you increase competition. And in the US, there are efforts by municipalities to start municipal broadband. It's a legislative fight. Some states allow it, some states don't allow it. But there also, if you have the last mile of fiber network, which then the ISPs can lease and compete, that's really the way
That's the political, not engineering. Like, what's the engineering?
So engineering is how do you do the leasing? How do you do unbundling at higher layers? There are some. I mean, I can talk offline, but unbundling is not that easy. Unbundling was tried and it failed for technical reasons in some other cases.
Logistics. In Greece, they tried to do this unbundling, and at the end, the incumbents, they will just delay your connection for 2 weeks.
They have no interest.
So
they have no interest or no incentive. So one thing, one scenario actually which might be interesting, and we might accidentally be in a lucky position, is that we have these islands of monopolies. Now, if we can design a scheme where technically it's feasible to do the unbundling with facilities owned by an incumbent, and you can design a pricing scheme where the leasing is priced properly, so that now that Time Warner and Comcast are not allowed to merge, can they go and compete in each other's markets? So that, I would say, is more of a pricing mechanism design question. But at a technical level, it's how do you do unbundling at higher layers, and how do you maintain quality of service? How do you ensure that things are how they should be? So a lot of measurement work is involved. There's effort by the CADA folks at MIT, Dave Clark and Casey Claffey. They're doing all this measurement to check where's the congestion, who's violating network neutrality, who's not.
Okay, let's end here.
Okay.
So, yeah, thank you, Vishal.